Hey everyone, so I just want to quickly go over how to set up horizontal projectile motions. This is one of the three different types of projectile motions we talk about. We already talked about vertical projectiles, and later on we're going to end up talking about angular projectiles. So what is horizontal projectile motion? Well, as the name implies, it's essentially when you give an object velocity only in the horizontal direction at first, and then you allow it to essentially experience gravity and fall to the earth like normal. Here, what we have to end up doing is we have to be very careful because motion in the horizontal direction is unaffected by motion in the vertical direction. What this really means, because of the fact that the x and y directions are independent of each other, and this is not just true about horizontal projectiles, but everything, because they're independent of each other, the velocity that we give the object is not affected by the acceleration of gravity pulling it down. All right. So the main idea is because of the fact that the X and Y are independent, what we have to do is when we organize our information, what we're going to have to do is take into account all the values that represent what's going on in the horizontal direction, all the values that represent what's going on in the vertical direction, and record them separately so that we don't confuse them. The idea is that we can't take a velocity, the horizontal velocity we give this object, and say that it's being exposed to the acceleration of gravity. So the way we're going to do this is we're going to make a little bit of a chart. Well, before I get to that, so I kind of hinted at this in class, but this is shown with the subscripts on the reference tables. Like I said, if you look at the reference table equations, for the first three motion equations, you'll see a lot of x terms in there, like this one, vx equals v naught x plus axt. What this is trying to say is to remind you that when you use this equation, because the velocities and acceleration are all vectors, they all have to represent vectors in the same dimension. So if this velocity is an x direction velocity, then this velocity also has to be an x direction velocity, and this acceleration has to be x direction. The same thing also applies if you want to replace the x's with y's to represent that they're all in the y direction. Now, you don't have to do this, but it might be useful, at least in the beginning, to note the subscripts to constantly remind yourself that these are all supposed to be a very specific dimension. If you do that, it might prevent you from making the mistake of taking that horizontal velocity and adding the acceleration effects to it, the vertical acceleration effects to it. Oh yeah, and then the last thing that says here is you'll notice that time doesn't have a subscript, and that's because time is a scalar. It is not really an x or y dimension thing anyway, and this allows us to end up combining the information from the two dimensions as almost like a linchpin. This is what kind of connects the two pieces of information. Because if we know the values that we can get for using the x direction to find the time, then we can use that time in the y direction because it doesn't matter which dimension we're using it with. Time is fluid and flexible like that. Actually said this before in class that a lot of times you're going to see problems where we almost have to use an equation in one set of information to find something and then use that again later on with a second scenario. And this is actually a perfect example of that. We'll see a bunch of examples of this later on. So here is a horizontal projectile. So we have an object being shot horizontally, and the object will end up falling to the earth along this parabolic path. There's a variety of different values. There's the height that it's usually launched at, and the distance or range that the object will end up reaching. Like I said, you do want to get into the habit of making an XY chart. Uh, if you get more comfortable with this stuff, you end up not having to make the full chart. Sometimes you might only make one part of the chart, the part that you know you can focus on. But at least in the beginning, think of this as almost like working with training wheels. You know, you got to practice the full method before you can kind of jump over and start doing kind of shortcut methods. So you make the XY chart, you write down all the given information. We already talked about these are the 6 main terms, variables in this unit: x naught x, v naught v, a t. And what you're going to do is just plug in information. Some of these information for the horizontal projectile are going to be, for the most part, constants. Like, for example, the initial position in the x direction is what we're going to almost always say is 0, because for the most part, we're going to start the projectile on the left side going to the right, and we're going to say that this is the origin, or I should say this point is the origin. If this was a graph, you can actually almost see the x and y sides here, but this is the origin, so it starts here, and then this is where it's going to end up landing, D being the final position. Now, sometimes they give you D, sometimes you're looking for D. That's why I just left it in there. We don't really know what that is. The initial velocity will go in for the x direction, but the initial velocity in the y will be 0, because again, the whole idea is that the object is given only velocity in the x direction. So none of it is going to be in the y direction. If there is a velocity in these two columns, that means that the object is being shot at an angle, not horizontal. So in a vertical projectile, all the velocity is in the vertical side, the y side, and nothing's in the x. In a horizontal, everything's in the x and nothing's in the y, kind of idea. Here, this is the starting position. So in the y direction, it's going to start at some height, and then it's going to end up falling to the ground, which is what we're going to define as 0, right? And then the acceleration are also constant terms. So there's acceleration is going to be 0, and y direction, the acceleration is going to be negative 9.8. Now, I guess I will end up saying this. So because the acceleration ends up being 0, we also know that once we have the initial velocity, the final velocity is also going to be the same number. We also know that. So that's kind of nice that we always have that second piece of information, just given the initial velocity. And I think that's about it. The interesting thing is when you look at the vertical values, they look exactly like a standard free fall problem. So what this really means is that when you're doing these problems, you can almost treat the vertical side as an object experiencing free fall, and then horizontally just treat it like an object moving at a constant speed. Um, and before I move on to the next question, I did want to say one thing is that you want to be fairly careful about dealing with the two sides. Like I said, the whole point of making this chart is to keep in mind that only one side can be used at a time. So if you start using this initial velocity, you have to use everything in this column. If you use this acceleration, it has to be used with all these terms. Sometimes it might be useful to cover it up, but after a while you start to get used to it. The one thing that will carry over between the two terms is time, as I said. So you'll actually see me use almost combine this into one single cell, because time can be used in the x column or in the y column. It's the same number regardless. One thing I did want to point out though is because of the fact that the acceleration in the x direction is 0, what this ends up meaning is that the x direction is very finicky, if you will, in the sense that if you're going to be using the X side, you have to make sure you have every single other piece of information. So if you're trying to find this final position in the X direction, you need to make sure that you know the initial velocity and the time as well. Basically, everything in this column has to be filled out in order for you to find the one thing that's missing. Y does not have that same restriction. You can have one or two things missing and you could still use it because acceleration's such a key part of a lot of our motion equations, but X does not work that way. So that's one nice thing, is that if you're going to end up using the X column or using X values, and that you're missing a little bit too much information in the X, it kind of hints as to what you have to find. You're going to have to find the time, you're going to have to find the velocity or something. But for the most part, they do give you a lot of the information, and you really shouldn't be finding yourself doing more than 2 steps in solving these problems. Like I said, the most common setup is that you use the y side to find time, and then use that time in the x side to find whatever they're looking for, the distance or the initial velocity. All right, here's the first question. Pause the video, work itself, and we'll go over in a second. All right. They want us to sketch 3 motion graphs just in the x direction. So we're going to end up doing one for the x and one in the y direction. So we're only looking at that x side of the column. And I like to start off with the acceleration. So the acceleration, where is it? The acceleration we know is a constant value, and it's constant 0 because there is no acceleration in the x direction. So it's constant 0. And because the acceleration is constant 0, then the velocity must be constant non-zero. So this will have a constant velocity that doesn't change, just as we saw in our chart. So it's going to start at some initial velocity, and because the acceleration is 0, the slope is going to be 0. So we just have a flat line like that. And then because this is a constant graph, this should end up being a linear graph. We say that the object starts at 0, and then because this graph is constant and positive, this graph will have a slope that's constant and positive. Keep in mind how I set this up. I start off with identifying the initial value point and then worry about what shape it is, right? So I realized that this started at 0 and then was constant because acceleration is always constant. I knew that this was started at some positive velocity value, and then I used the acceleration to realize it was a flat line. I realized that this started at 0 because that's how we defined x naught, and then I used this graph to realize, that it was linear and that it went up. So keep that in mind, that a lot of times when you're doing these sketches and you're coming up with graphs, sometimes it's useful to plot out certain points where the graph starts, where it's going to end, maybe any points where that it's going to cross the 0 line, and then worry about whether or not it's supposed to be a straight line, a linear line, or a curved line, right? Here's the next one. Pause the video, work itself. I'm gonna go in a second. All right, so same thing. We want it this time in the y direction. Again, the acceleration is going to be constant. This time it is an actual value. It's non-zero acceleration. And we know that the acceleration is always -10. So it starts at -10 and then it should just be constant. We know that the velocity in the y direction starts off at 0 because it's horizontal. So everything's in the horizontal direction. And we know that because this is a constant graph, this should be linear. It could be linear up or linear down, but because this acceleration is constant negative, then this slope should be constant negative. So I do a constant negative slope. With this, I now know that this is a curved graph. I know that in the vertical direction, realistically, this should have been y versus t and y versus t. I apologize. But in the y direction, it starts at some positive y value. I know it's going to end up going to 0. The question is, does it go straight or, well, I know it already goes curved, but is it going to go curved this way, concave down, or concave up? Because of the fact that this starts off with 0 velocity, this should start off with a 0 slope, meaning it should just start off flat initially and then get pointed down more negative. So this is what the graph looks like. The really nice thing, this is exactly the same parabola that we see when we actually see a projectile being launched horizontally. So it actually works out really well. And that's what we end up getting. All right. Here's the next one. Pause the video, work itself, and we'll go in a second. All right. So they want us to figure out how long it takes for the arrow to hit the ground and how far from the shooter it lands. So again, we're going to fill out the values into the chart. Here's all the information. We have the three, well, not the three, but the 4 pieces of information that are always the same. Five pieces that are always the same. With the initial velocity of 200 in the x, we also know that the 200 velocity in the y, the final velocity is 200 meters per second in the x. We know the initial position in the y direction is 1.5, and this is what we're looking for. Now, again, if we're looking, well, actually, they first want to know how long it is, so time. Because of the fact that I have 2 pieces of unknown information in the x column, I can't use the x column, so I have to use the y column. So I'm only using the y column here. What I'm going to end up doing is I'm going to take the annoying x equation and slightly change it to replace the values with y to remind myself that I'm doing y terms, that I'm using the y side. This is one way to help kind of organize your equation so that when you're looking back at your work or working through it, you can identify what information is related to what setup of the chart. So y equals y naught plus v naught t plus 1 f a t squared. We have all the terms. We're just going to plug them in, and then we get our answer of 0.548. Then to figure out how far from the shooter does the arrow land, That's this X term. Now that I have the time, I now have all the information I need in the X column. So I'm going to use the annoying X again. This time, X equals X naught plus yada, yada, yada. Using all the X terms, plug them in, and I end up getting 109.6. Again, keep in mind that I'm using only the X column. So the acceleration is 0 when I did it in part B. And then in part A, the initial velocity was 0 because that's what it is in the Y column. All right, so we're going to leave it there and do the rest of the stuff about horizontal projectiles in class. The main takeaway is to make sure that you keep in mind how to set up the XY charts and when to use which side, things like that. For the most part, it is really straightforward. There really aren't that many twists and turns when it comes to horizontal projectiles. So that's it. If you have any questions, feel free to let me know. Otherwise, good luck. Having a great day.